Okay, great presentation, Dr. Floyd. Thank you very much. So now we're going to switch gears and hear a little bit about smartphone-based networks for roadway condition monitoring and early warning system. It's my pleasure to introduce Nasim Uddin from the, I hope I said your last name correctly, from the University of Alabama. Nasim is a professor and graduate program director of civil engineering at the University of Alabama, Birmingham. His research interests include UAVs and robotics, disaster risk management, and structural safety. So with that, Nasim, the floor is yours.
So good afternoon, ladies and gentlemen. It's my pleasure to be here. Like Dr. Athur Azizi Amini, I'm also a graduate student of University of Oklahoma, Norman. And thank you so much, Dr. Jaman, to have me as a student 35 years ago and inviting me again to come and see Norman, Oklahoma and Oklahoma City again. So thank you so much for all those you did. So my title is a little bit different. I want to focus more on the bridge than roadway, even though the technology I'm going to present is also going to cover the other aspect of the roadway network. So today I'm going to talk about really the digital twin system that we can use for the bridge management and the post-hazard assessment that Dr. Aziz Amini mentioned about so passionately, that we really need new technology, and hopefully I'm going to show you some really new technology today. So issue with the bridge actually, as you know, as the bridge infrastructure getting more and more older. For example, we have an average design life 50 years, but we're going to have 25% of the bridge within 10 years, 65 years older. So as the bridge getting more and more older, the funding to fix them actually getting lower and lower. So you really have a bad catch-up game we have to play here. So in order to combat these situations, that situation gets more worse because we have not only the asset management that's going to cost over $2 trillion. On top of that, with the climate change, with the extreme change of heat and cold, and also with the different hazards like earthquake, the hurricane, increasingly getting higher and higher in numbers, we're going to have a really double-sword problems. And that really causes us to think outside of the box, because the state of the art that we have for the maintenance and inspections is completely obsolete. It's not going to be working very well as more and more bridges having maintenance problems. And also after earthquake or hurricane, we don't have that state-of-the-art technology to quickly know the hidden damage and also the system-level problem that we have. So in summary, the state-of-the-art technology is completely incapable of right now to catch up with this large volume of maintenance challenges and hazard-related challenges that we are going to face. So therefore, we have to look outside the box and some new excellent technology. And one of them being tried is the digital twin. It's a very cool idea. What you do, you take the real environment on the right side, real world, and you create a virtual simulation world. And in the simulation, you try to update and calibrate based on the real data so that over the time, with machine learning and with the data analytics, your simulation gets better and better and better, not only to predict the current situations, also to forecast what's going to happen over the time. This is very appropriate for the bridge infrastructure because here what we can do, you see the left side, the real bridge, we can make a mechanics-based model, for example, finite element, based on the design and construction of the bridge. Now imagine with the collection of the traffic data and other hazard data, we can continuously update the model in a situation that it will replicate, give you the same data you can see real time. Now you have the tool you can use to extend your view to see when you're going to need the maintenance, how much it's going to cost, and what's going to happen if something else happens, like hurricane or earthquake. So this really gives you an amazing tool to plan ahead and budget ahead. Especially this is feasible because of some advancement in technology in number of areas. And all these three areas, actually, I've been working last 35 years, mostly funded by NSF. So we have some really groundbreaking, problem-solving results that we did in all three areas of direct measurement on the bridges, the indirect measurements on the bridges, and the drive-by inspection. So these three technologies now matured enough to give us enough confidence that we can do a good job on a digital twin idea. So let me tell you a few of those groundbreaking ideas or solutions that we could come across. On the direct, the idea was really how you bring all those three approaches together to serve the digital twin idea. On the direct measurement, one of the problems was actually that if you put a sensor, you need electricity. Now, not all the bridges has access to the electricity. None of them, very few of them. Also, if you have a sensor, it keeps on collecting the data 24/7, and DOT doesn't like it, because then if something goes wrong, it's become a liability because they don't have the manpower to analyze all the data all the time. And thirdly, all the sensors, they're giving you the one side of the data, like how good is the bridge is. It doesn't give you the data on the loading side of the bridge, how much load the bridge is carrying. So that part of the equation was always missing. So these three bottlenecks, we could solve, and I'm going to share with you how we solved them. Here, if you don't have electricity in a bridge, you put your sensor, then what's going to happen, we're going to have a pad, we're going to be installed on the bridge, and then the drone going to come, they're going to charge up the sensor for one next cycle, and also upload the data, right? And then go home. So now you solve electricity problem, and also you solve of having not too much data. You only get the data when you need. We also go next step. Before even that, I'd like to share with you some detail on the pad, how this pad works in terms of collecting the data and then transmitting the power. Now, we also went the next stage. In the next stage, we converted the drone as a sensor. So inside the drone, you have this sensor, so it attached to the bridge and acting like a sensor. So you don't have to really take the effort to put all those labor, all the maintenance issue, all the issue with the sensing is all gone. You just, fly the drone and it acted as a sensors. Another work we did actually, if you have an issue with attaching the sensor in the bridge, we created contactless sensing. In this sensing, you don't have to do anything on the bridge. So you have a drone hovering close to the bridge, and through the image it captured, we can get the sensing data, vibration, the displacement. We can also have our camera away from the bridge on the right side of the picture, and we can get the data we need. Now this data, the good part of it is not only going to give you the strength of the bridge data, but something else. And that something actually is the weight of the truck itself. So what we did, we converted the bridge into a scale. So as the truck goes over the bridge, like a scale from the data that we collect before about the strength of the bridge, we use the same data to get the weight of the truck going over the bridge. One of the challenges we have actually, what happened if you have a multiple truck? That was a big problem for us, and it took us a while to solve that. And in the next slide, you're going to see that this is what happened. So you have a multiple truck going through the bridge, and once again, we are able to collect the data like I showed you before with the direct measurements, and use those same data, we calculate the weight of the truck. And the result was within 2 to 3% accuracy level. And these are some of the results. So it's very comfortable within the range. Now that's the direct measurements. And also one of the problems we solved is to see what kind of truck is going over the bridge. So we knew exactly what types of truck are those. And also we could calculate their velocity, the distance between the truck, and all other traffic information. So now you have the data on the strength of the bridge, data on the load of the truck. Also you have the data on the types of the vehicle and the distance and velocity. We pretty much have everything you need. So that's really going to fit to the digital twin and going to give you a really accurate representation of the actual bridge structures. That's the idea. Now, in the indirect measurements, we use some robotics. Like indirect measurement means that you are using the data, using the model shape to figure out where is the damage in the bridge and the location of the bridge. So here, for example, we have some small robot moving through the bridge, collecting the data, and then you get the data. And on the left side, let's see if it works.
Sensor performance, field testing.
Yeah. So you see the drone is moving, right? Let me go back again. Yeah, it has been a challenge to run those slides. Just give me a second.
Sensor performance, field testing is carried out.
See, on the left side, you see again the robot is moving with a sensor along the cross bridge and getting the data. So based on those data, we can really calculate the mode shape, and from the mode shape, we can get the damage locations and the damage estimation. Another work we did here, I hope, is with a smartphone. That was my more motivation of this presentation. I hope it's going to run now. So if you look carefully, we just put a smartphone on the bridge. And as the smartphone is collecting the data, vibration data from the vehicle moving across the bridge, these data are very raw data. So we come up with a very sophisticated algorithm. I don't have time to went through that. It's a physics-based, we call stochastic resonance modeling. This filtering technique converted this raw signal of a smartphone into a very high-quality signal. From there, from the shifting of the frequency, we could estimate the location of the damage and extent of the damage. You know, that was really the cool technology that we could develop. And also, this is something people are doing actually, many other people. We could get the data of the drone moving around the bridge and get the data on the cracks and the location of the cracks. And again, it can differentiate between the shadow and the real crack without any problems. Then finally, the drive-by inspection. This is actually, we have been the driving force in this technology. If you look at the figure here, we put the sensor not on the bridge, inside the vehicle, in the axle. So as the vehicle moves, it collects the data from the vehicle, and from the vehicle data, you could see in the blue color, we can see the frequency of the bridge. And from extracting that frequency, we could estimate the state of the health of the bridge and its future damage potentiality. So this is really a real experiment we did in the lab, where we have a bridge damaged, and we have a truck moving through it, collecting the data. And from the data, we could, again, if you see the damage location on the bridge, in the next slide, we could really identify the location of the damage and the extent of the damage. So this is the drive-by inspection that really coming very, very strong. So with this, and I showed you the direct assessment, indirect assessment, and then drive-by inspection. If you bring all of those things now in a real bridge situations, right? Here you have, on the left side, we are collecting the direct data. Then in the middle, you are collecting those intermediate or indirect data. Then from the camera, you are getting the information about the vehicle type, its load, its velocity. If you feed all of them into the mechanics-based model, say finite element model, now you have a model that can give you the real-time performance. Then also you can use it now for future situations, right? What's going to be the maintenance requirement and what's going to happen if some disaster, extreme event comes. So here, an example of the exercise. You see on the digital wheel how the bridge is performing in the time, how we are collecting the data and going to the cloud, and then how we are predicting if some anomalies comes, some future problem happen, how this bridge is going to perform. So you can have this kind of assessment today, right, if you have that kind of model in the digital twin environment. So this is another study done by my student at USL, UCLA, and they have this bridge, collecting the data, develop the digital twin, and then they could actually, based on the data collected, they could estimate the different level of damage on the slab, the different level of damage on the tendons, on the deck, on the girders. They could backfigure all of them just based on the collecting the data in the real time and feeding them into the FEM model. Not only that, once this model is well done and giving the good estimation, they use it to predict how this bridge is going to perform for different level of earthquake. So they did a parametric studies and they identified the need of the maintenance and identify the level of inspection, all which are needed, and then come up with this performance in a different level of disasters. So all of those things actually now is practicable. All of those are possible. Actually, the idea is to do more field study, more experimentation to calibrate and to really perfect all those technology I just shared with you. So this is my presentations and some of the project, as I said, mostly funded by NSF and some, DOT, some of them. And I have some publication I'm going to be listing with the presentations that you can look up to know more about those technology I shared with you. So again, in summary, actually, that the new times are here, new technologies are here. Actually, this is a challenge to Oklahoma DOT and Federal Highway to really embrace those new technology and give this technology a chance to prove to you that they work. If we don't give those technology a chance, it's not going to work, right? With that, I want to challenge all the DOTs to come and embrace those technology and try them out. And hopefully the new paradigm gonna come and we can do a better job in managing and maintaining those bridge infrastructures. Thank you so much for your attention, and thank you again. See you some other time. Thank you.